Okay, can you please check, Mr. Nelson? All right, so because my students said that they have not seen it, I interrupted it. So this is another presentation that I'm going to do. So anyway, my dear students, you are in my live lecture on buoyancy and stability of submerged and floating bodies. Okay, I had given you a copy of this before, but there are some homework and some questions that I want you to do from this topic. This will be the first topic in the finals. Nelson, Mr. Manuel, Mr. Ibia, can you please check if it's already working? I have to redo it. All right, so I have, as I've said a while ago, in buoyancy, it's all about bodies that are going to be submerged and float. Okay, so the stability of some bodies that are floating, that will be the second part. The first part we're going to do will be just be the buoyancy. All right, thank you, BM. So as you can see in here, I've got a shape. Okay, a shape is on its neutral position where the G, the center of gravity of the shape, and the center of buoyancy is there. On the second illustration, which I have already mentioned a while ago, because but due to technical problem, then of course we have to redo it. There is a shift of your BO to B. The center of gravity will still be there. The metacenter will occur when your ship tilts. The metacenter will be a point of reference for the shape or the floating body to go back to its place. Okay, right. This will be the second part. But first off, we have to do the Archimedes principle. The Archimedes principle is the one I was explaining a while back. It involves submerged object in a fluid, and the Archimedes force, the buoyant force in the Archimedes principle is always an upward force. And this is equal to the weight of the fluid it displaces. I will explain more on this with an example. The formula we're going to use will be FB, or the buoyant force, is equal to the mass density of the fluid times the volume of the displaced liquid times G. What is the displaced liquid? If you're going to submerge a body in water, the one that is being wetted, the wetted area. So for example, this one, or wetted volume. If I'm going to put this in water, and this is the only part that is wet here, here, here. So that will be the volume you're going to consider. But if all of this goes down the water, it's fully submerged, then all of this area and height, the volume, will be the one to be computed for the V. You will know more about this with an example. The FG here is this one. The FG here is the force due to gravity, which is actually the weight of the body. Okay, weight of the body, which has the same formula, the rho times V times G. Okay, now moving forward. Buoyancy in submerged bodies. Okay, so let me just read it for you, or you can read it with me. Buoyant force. For a completely submerged body, the buoyant force is equal to the weight of the fluid displaced by the body. So for fully submerged, the buoyant force is equal to the weight of the fluid. And the formula is buoyant force. Sorry, I have already calculated this earlier one. So buoyant force is equal to the density of the fluid, the volume, and the acceleration due to gravity. If we're going to evaluate the unit of the buoyant force, because it's a force, then it must be in Newton unit, right? So Let's investigate the units. The rho, the rho F, or the density of the fluid, is in kilogram per cubic meter. The volume is in cubic meter, and the acceleration due to gravity is meter per second square, right? The meter cube cancels out, so you're only left with kilogram meter per second square, which is actually Newton. Okay, so that would be the unit for the buoyant force. Again, buoyant force is the one that pushes the body up. Okay, but if it's not enough because the weight is too heavy, then matatalo ang buoyant force. What happens? The body will sink. Okay, but if the buoyant force is so great that the weight is just light, then by summation of forces vertical, then um, the body will float. By the way, the buoyancy is the first topic for finals. Okay, but well, with the so many um, missed classes because of the typhoon, well, this is fortuitous event. Then of course we cannot blame anybody, but this is nature, so we have to rush. Okay, whether we like it or not, we have to cover a lot of topics that we have missed. All right, so if the buoyant force is less than, if the buoyant force is here, this is the buoyant force. Okay, that will be less than the fluid, the rho of the fluid, then hang on. The rho, I'm not talking about the buoyant force, I'm talking about the density. Okay, if the density of the fluid is greater than the density of the body, this is for the body, the yellow one, then it floats. But if the density of the fluid is lesser than the density of the body, then it sinks. Okay, so if this is the one that we're going to throw to a body of water, then of course this is lighter than water. It floats. But when it gets saturated, when water gets in it, then of course it sinks, right? Okay, so let's have one example here. This is an oak cube. What is an oak? O A K. O-A-K. Oak is a wood from an oak tree. I researched about what oak is. And oak wood is a popular, just for you to have a notion about it, will not just say this is an oak wood and it has a specific gravity of blah, blah, blah. No. So an oak wood is a popular and versatile type of hard wood known for its strength, durability, and distinct appearance. And it has a relatively high density. Why relative? Relative because when it's dry, then it can have 600 kilogram per cubic meter density. But when it's saturated or it has moisture content, it can be as heavy as 900 kilogram per cubic meter. So it's a relative high density wood. Okay, so it's relative, as I've said, because it depends on the situation. It is hard, and it's resistant resistant to wear and tear. So it's a nice kind of wood. The color is between white oak to red oak. And then the grain, it has a straight grains, workability is durable, and so on. Okay, why am I saying this? Let's go to the uses. The uses of oak tree is for boats and barrels. There you go. And that is what we are trying to learn in here. What, but of course not the materials, but how could these materials behave in different kinds of fluid where they float. So it's a water resistant and used in shipbuilding and wine or whiskey barrels. Okay, that's why wood could be the very prominent or popular material we will be using for our buoyancy and stability topic, because we will be analyzing behavior of boats or ships that are on water. Of course, not on land, but on water. Okay, so what are the buoyancy types in here? When it's partially submerged, when that awkward is partially submerged, or fully submerged. Okay, so let's have an example. Where's my example? Here you go. Right, here. So there's an oak cube with a row of 740 kilogram per cubic meter. If you remembered what I have shown you a while ago, the oak has got 602. Anyone? As if I heard Mr. Abel saying it. 600 to 900 kilogram per cubic meter. Okay, relative, because it depends on the situation, whether it's a dry one or it's a wet one. Okay, so we have 740 kilogram per cubic row or the density, and this cube has a size of 7. It has a size of 7 centimeters. It has a row of 740, and we are talking about an oak wood. Now, we had a formula earlier on that we have to compare this formula for the force due to the weight and the force due to the buoyant force. Okay. Now, for the wood itself, Fg would be 740 kilogram per cubic meter. That is our row. Our volume submerged is 0.07 cubic meter. Why? Because we have changed the 7 centimeters by 7 centimeters by 7 centimeters to its meter equivalent. So when it's meter equivalent, the 7 centimeters will go, the decimal point will go twice to the left, 1, 2. And the new position will be there, and you put a 0. Then this will give us a meter unit, because you have to divide by 100. Okay, so 0.07 meter cube times 9.81 meter per second square. Do you have any problem? Mr. De Gia, please go to, Mr. Agustin, please go to YouTube. MJ Villafuerte, thank you. Mr. Morales, go to the YouTube now. Okay, so if we're going to compute this, we have 740 kilogram per cubic meter times 0.07 cube. There you go. That is already the sides of the square. You're going to cube it, yeah, because it's length, width, and the height, times 9.81, sorry for that, times 9.81, that is the acceleration due to gravity, and you will have 24.899. That's it. Hey, what happened? Oh, I made a mistake. I typed in 7,500. What is this mistake all about? Hey, I'll do it again. Sorry for that. 740. I put another thing in. Well, oh, why? Why is it giving me another? Okay, 740 times 0.07 cube, and then multiply it by 9.81. I know you are shouting there. Times 9.81. I know you're shouting there, Mom, you inputted another one. Okay, so it gives us 2.4899 or 2.5. They have rounded it up, but please don't do this in the exam. Let it be 3 decimal places, 4 decimal places, as the case may be, but we are safe with 3 decimal places. But for mechanical students, as I've said, let's go with your your requirement, which is 4 decimal places. In this case, it will be 2.49 or 2.490, or rounded up to 2.5. Okay, so that will be the force. As you can see here, the force due to the weight. We have to compare them always. So the next thing is, let's put in here. Let's put another slide in here. Okay, and let's type in, let's write the force due to gravity, which is equal to weight, is equal to 2.5 newtons. We still need the force due to buoyancy. Now, there's another way to get 2.5 actually. So I'll show you how. Hang on, I have an outline for that. Okay, so another way to solve weight of wood, or that is the force due to gravity. Of course, we know the sides of the wood to be, I'll use this color. The side is 7 centimeters. To convert that to meter, you have 0.07. Solve for the volume, that is, of course, the length, the width times the height. So because they are all the same, you have side cube. Then you cube that. Don't do this one, okay? Because if you will be missing a zero, like what I did a while ago, there was an extra zero, it will make the answer incorrect. And then we know that the density of an oak from the given is 740, okay? But they said that it's 600 up to 900. It depends on the moisture content, okay? Now, the mass of the wood from the formula, rho is equal to m over v, because this is in kilogram per cubic meter. That is the unit for the rho. Then you can get m from here. M is equal to rho v, correct? So our rho is given, that is 740 kilogram per cubic meter. We know the v, which is 0.07 cube. Then you will get what? The mass of the wood. Now, we go back to the formula. W is equal to m times g. Are common when you're going to round it up to first decimal place, which is 2.5. So that's also one way of doing it. But for the buoyant force, if you notice, the weight will already be rho, v, and g. Okay, so that's a straightforward formula to find for the weight of the wood, which is equal to the buoyant force formula. Okay, so I hope justice on the two ways and how to compute for the force due to the weight, force due to gravity. Next, the next thing to do is to find for the buoyant force. For the buoyant force itself, you can see from here, it is rho. Oh, that is too thick pen. Okay, the rho, the v, and the g. All right. Why is the v 0.07? Because it's fully submerged. As you can see here, all the parts of the block, they are all wet. So if they are wet, then the length, the width, and the height will be the maximum volume. But what matters here now and makes a difference would be what? The 1,000 kilogram. Why? Because you are already pertaining to the buoyant force, the force that pushes the block up, correct? All right, so it's 1,000 times 9.807 cube. Okay, let's put that in here. So the buoyant force will be 1,000 kilogram per cubic meter. This is already about the liquid that is pushing the block up and is fully submerged. That is the buoyant force. This is your Fg, okay? And it's fully submerged. It's underwater. So for the formula, it is rho volume G for both weight FG and FB. Then the rho is 1000, the volume is 0.07 cube, and this is meter cube afterwards. And then you have to multiply it by 9.81 meter per second square. At the moment, I cannot see your comments. If there are comments in there, I'll just have to read them after my lecture, because I am sharing my screen to you. So it's a full screen in my, if you can see it here, there you go. It's a full screen in my laptop. I don't have any space for the comments, but I know that you have some comments in there. All right, so let's compute this one then. I'll bring up my calculator. It's Casio. It's 1000 times 0.07 cube. There you go. And then multiply it by 9.81. And what do you think will be the answer? Okay, so we got 3.3648. There. Now we compare 2.5 and 3.3648. Your force due to gravity is just 2.5, pushing it down. And the force due to buoyancy is 3.3648. So, mas malaki ang pag-push up niya. All right? However, it's not going to float on the surface. It could be floating inside. So this is like, okay, here's the water surface. Your block is here, but it doesn't go sink in down to the rock bottom. No. Okay? So it's just floating somewhere here. So that is the buoyant force. And this is the force due to gravity, or this is equal to the weight of the block. Okay, I hope you understood that. Now, let's go to a situation where the block will just be partially submerged. If it's partially submerged, will it float throughout or will it sink after? Okay. So I have here a situation where the oak cube has been sank in the water 4 centimeters from the surface, as you can see from this illustration. Can you, I am like running after my breath or what here. Yeah. So it's 4 centimeters from the surface of the water. Now, everything holds true, all conditions, like the density of water is still 1000 cubic. It's still 1000 cubic per kilogram per cubic meter. The volume this time will be it's not 0.04. Okay. The volume will be not 0.04. That will be, each side is 0.07, right? So it will be 0.07 times 0.07 times 0.04. That is a submerged. That is a submerged volume. So let's compute that. What is the submerged volume? 0.07 times 0.07 times 0.04. 0.04. Okay, look at my values. Then it gives us, oh, look at that one. Why is it like that? It's just 0.04. There. Okay. So that is 0.00196. 0.000196. So it is 1.96, yeah, in the scientific notation. Yes, 1.96 times 10 to the negative 4. It means there are 3 zeros before the 3 significant figures. So it's 0.00196. And let's put it here, 0.000196. There you go. So the buoyant force will now be 1000. That's for the liquid. 0.000196.00916. That will be for the volume. 9.81 for the G. So what will be the buoyant force value? Let's calculate. Bring out the calculator here. So it's 1000 times point no 0.000196. Look at my values in the calculator if it's correct. Times 9.81 equals. There you go. It's 1.92276, 9228. And what's the unit? Newtons. All right, now we compare. The buoyant force is 0. Sorry, not 0. 1.9228. 1.9228 newtons. And the weight of the block due to gravity is 2.5. It means that the weight is more, correct? It's more than the buoyant force. What will happen? Of course, it will sink. Okay? It sinks. You don't put it straight away down because it takes some time to go down as well. Okay? When you throw that block, it will be 4 centimeters meantime, but after sometimes it sinks because the weight is greater than the buoyant force. All right, so that is if a body sinks or floats. Okay. Now, I have some questions here. How to make the awkward float? Just a short trivia questions. Which of the following materials, when attached to awkward, can help it float? What happens to the buoyant force when you hollow out a piece of awkward? What does it mean? When you hollow out, for example, this is a bangka, right? Rectangular. You are seated here. This is sinking. Why? Because the buoyant force is not enough for it to lift it up. Because the body is dense. What do you do? It says here, you're going to hollow it out. What does it mean? You're going to cut some portions. Okay, so how does it look like after? Maybe it looks like this. There, and then you can sit here already. So by hollowing out some parts of the wood and submerge this to water, then the density can also be lessened. The density of your wood can be lessened, so it floats after. Okay, it floats on water. Okay, so which of the following statements can make the awkward float? And here, number 3, how does sealing airtight containers to awkward make it float? Number 4, number 5, you can read them. Please answer them and give me these answers. This will be your homework 3 because there are 2 homeworks down the slides. This will be your homework 3, 1, 2, 3, 4, 5 questions. Just put the letters only. Okay, example only. This is homework 3. Answer the trivia questions. Okay, that's not there. Right. Homework 1 in your notebook is similar to what I have discussed. It's also an awkward. Okay, let's not go anywhere anymore or put any other thing. So you will get the hang of it. So it's still an awkward block, and it has these dimensions, 20 by 10 by 5. It has 750 kilogram per cubic meter as its density, and it will be submerged in a fresh water. If the block floats with its longest side, so it means the 20, So how will it look like? So it will float on the longest side. So this is how it will be submerged. Okay. Horizontal and 4 meters submerged, longest side, and 4 centimeters will be submerged. What is the height of the, what is its height? If this is 20, this is 10, this is 5, right? So there will be like 1 centimeter off from water. 4 centimeters is submerged, it says. So you have to calculate the volume or determine the volume of the water displaced. You have to determine the buoyant force acting on the block, and you have to determine whether it will float or it will sink. Okay, you have to use the formula that I have introduced or I have used earlier on this slide. So that's homework 1. Homework 2 is this one. It's similar, but now it will be in air. It's not in water. Okay, air will be the fluid here. The answers for your guide are here. That is what is a bonus for you. Okay, so you have the answers for your guide, so you can be more confident whether you are doing the right um, solution or not. Okay, so this is what I want to extend to you all this day. And there you go. So I now I'm here. I'm actually in the house because in the office it has a very poor internet connection. So sorry for my husband. What are the comments? Ma'am, sobra yung na-input mo sa row. Yeah, I know. It should be 7,000. It should not be 7,400. It's 740. Okay, any other comment, my dears? Yeah, any other comment? So, yeah, it's 32 past, and I guess everything is okay. You've got 3 homeworks, but I'm going to send it now. I'm going to send the video of this, the video clip, and also the PDF file of my lecture. Okay? So you have 3 homeworks. 3 homeworks. The part 2 will be given maybe tomorrow or anytime within the week. The part 2, which is the stability, where you have the tilting and you have the meta center, the BO, the B, and so on. Okay. All right then. Thank you so much for listening. Thank you for being with me during the lecture. If you have some questions, you just have to PM me, and please help each other to solve it. Share, because we need to share now because we have been we had been visited by a lot of calamities. So my God, this is just to cope and to finish the curriculum, inshallah. Right. Bye for now, my dear students, and see you in the uni tomorrow. And the exam will be on Monday. Bye for now. God bless you all.